guys, in the previous video we covered the simple pendulum, and in this video we're going to be covering the physical pendulum. All right, now what is the difference between them? Because they both say pendulum, so what is the difference? How do I know if one is simple versus physical? How do I tell? All right, a simple pendulum is one where all of the mass is concentrated in a small object right at the end of some string. All right, the string needs to be of basically negligible mass compared to the object at the end, and also the dimensions of the object, which is swinging back and forth, need to be negligible compared to the length of the pendulum arm. For a physical pendulum, neither of those, or at least one of those assumptions, is incorrect. All right. So what I've drawn here is something like, imagine a meter stick kind of a thing, whatever, a rod of some kind, where the pivot point is here, and it's, oscillating back and forth. That is not a simple pendulum in any way because you have mass distributed all along the length of the object, and the dimensions of the pendulum arm, which really would just be this distance here, are definitely not negligible compared to the dimensions of the object. In fact, in this case, they are smaller than it. All right, that won't always be the case, but neither of the assumptions that we mentioned for this one are in fact true of this system here. For a physical pendulum, you will start things off kind of like how we did the simple pendulum, except for one incredibly significant difference, and that is this. We don't start with forces. For a physical pendulum, you have to begin by talking about torque. Way back in the rotation unit, right, we did the falling bar problem, right, where you'd have, all right, the bar out here, there's a pivot, and it goes, right, you had to figure out things like, all right, the angular acceleration and the maximum speed when it gets to the bottom, all that kind of stuff. And in order to talk about the acceleration of it, you had to bring up the concept of torque. All right, now you hopefully recall that torque is F cross R. That cross product meant that the torque was proportional to the sine of the angle between the force, which is causing the bar to rotate, and the distance between the point of application of the force and the pivot point. All right, now the torque acting on the force acting on the bar is going to be the force of gravity. That force acts at that distance, let's call it D, and it's going to be initially at some angle theta from the vertical. So that small angle there we'll call theta. All right? The torque, therefore, is going to be mg times d, and then times sine theta. If you recall, sometimes there's some confusion with falling bar problems. Which theta am I supposed to be using? I don't know. All right. The way that you decide is you draw arrows which are the radial vector and the force vector, all right? And then you see what angle they make between them, all right? Here's our radial vector. I drew it longer than I needed to, but that's for, I guess, emphasis. And there's my force vector. This angle, theta, is the angle that I started with. Okay, so mgd sine theta is going to be our function. Next, we set the sum of the torques always equal to, if you recall, I alpha, which is analogous to ma, right? The sum of the forces is ma. The sum of the torques is I alpha. All right, next step. Just like when we did the simple pendulum, we'll be able to say that sine of theta it's equal to theta as long as theta is small, right? If you don't remember what I'm talking about, you can go back and watch the simple pendulum video, but recall it's called the small angle approximation. We'll say that sine theta is basically equal to theta, as long as theta is small. So here we got mg d theta equals I alpha. All right, another substitution is same as we did for the simple pendulum. Alpha is the second derivative of theta. And also, remember, we've got to somehow get a negative sign in here because it has to look like negative omega squared, some kind of position equals second derivative of that same kind of position. So somehow we need to have a negative sign in here. Kind of insert it wherever you feel like, but the idea here is that the torque that's acting is a restoring torque, which is going to push the system back towards the equilibrium position, which is to say, hanging vertically. All right, we're almost there. I need to get the d squared theta dt squared alone for it to be of the proper format. So I'll just divide over the moment of inertia, and here we have our final equation. Okay, now if you recall, since it is of this form, omega squared is the mgd over I. So therefore, the period of oscillation for a physical pendulum, which is given for anything by 2 pi over omega, specifically for a physical pendulum is going to be 2 pi times the square root of I over mgd. All right, now there's some other details that we've got to flesh out here. One of those is exactly what do you mean by I, Mr. Errico? What is I in this case? Well, I depends on the moment of inertia, I is the moment of inertia of the object. Okay, but careful here. If we say this is a rod, and I say, well, a rod about its center of mass is 1/12 ml squared, I guess I'll put that in for I. Nope, sorry, that's not going to be right. Is this bar rotating about its center of mass? Well, I think it's fairly obvious from the picture that it can't be. If you put a pivot right through the center of mass, it would sit there. It wouldn't do anything. It wouldn't oscillate back and forth. It would just sit there. And so the pivot always, if it's a physical pendulum and therefore will swing back and forth, the pivot will be at a different position besides the center of mass. And therefore, the moment of inertia will always be given by the parallel axis theorem, which is that equation there. All right, so always the moment of inertia is going to be something that you'll find using the parallel axis theorem. Okay, so if we've got a particular scenario, obviously we'd be plugging in values of one kind or another. But this equation right here can kind of automatically tell us a couple of things about an oscillating physical pendulum. One of them is actually the mass of the pendulum doesn't matter. This has mass in it. There's mass again, and mass down on the bottom. So just like for the simple pendulum, mass ends up canceling out. It's just not actually as obvious because this equation does make it look like the mass is important. Actually, no. If I made this particular pendulum out of steel or wood, but I used the exact same dimensions, there would be no difference in the period of oscillation. All right, the other thing is the degree to which the period depends on this dimension d is a little bit ambiguous because you've got some constant plus md squared up here, but then d to the first power down there. The period has a complicated relationship with that distance d, okay? If d is really small, like, tiny little number down here, then md squared is negligible compared to this value right here. And therefore, you're going to have a really long period because you've got tiny number down here and basically just ICM up there. If d is some larger value, then you're going to have a shorter period up to a point. If d is large enough, then md squared becomes the dominant term, right? Much, much greater than ICM if d is really big, okay? And so then ultimately this equation would simplify down to, oh, actually, the simple pendulum all over again. Sure, do the math, all right? If ICM is basically negligible compared to MD squared, then this is what we have. We said mass cancels out, and one factor of D cancels out. This looks just like the L over G that we had for the simple pendulum. Okay, so in other words, if you've got a physical pendulum, but actually D, that value D, the distance between the center of mass and the pivot, is large enough, meaning it's somewhere way up here off of the object, then it's actually just a simple pendulum all over again. All right, now if you're dealing with any of the middle cases, you'd have to explicitly calculate it to see how it varies with distance, okay? But in general, that is our relationship, and please remember that for your moment of inertia term up there, it is never just ICM, it's always got that plus MD squared in there. All right, I thought it would be instructive if you guys actually got to see a physical pendulum and see some of those dependencies that I'm talking about. So that's a pendulum. Oh, you just can't see the meter stick. There it is. Okay, so now I've got it set up here so that the pivot is basically all the way at the end of the meter stick. And all right, now I don't have a stopwatch out, but you could, if you wanted to, measure the amount of time, and there you are. You could get the period from that. All right, now let's take it and put the pivot a lot closer to the center of mass. Can you even see that moving anymore? Oh, hang on. Let's try again. All right. Okay, now I know there's some friction at the pivot that's also tending to make it slow down, but you can see that when D was much, much smaller, the period of oscillation was much, much greater, and that fits with that equation that we had written on the board, where if D, which is in the denominator, is a really small number, then you're going to get a large period because you're dividing by a small number. Okay, well there's that. All right, well that is, I believe, everything we need to know by way of introduction to the physical pendulum. So I hope this video was instructive, and there will be more to come for sure. All right, thanks guys.